If then fine. Oh dear, that's very loud. Yes. Okay. Oh, still. Why don't we just? Yeah. Okay. Okay. All right. So you're only stuck with me for 1 more hour. So everybody should, look forward to that, I think. So we finished last time with the proof of full asymptotics for the local density of states for a one-dimensional periodic Schrodinger operator with smooth potential. And we realized that the main feature that you have in one dimension, which you do not have in higher dimensions, is that the only quote unquote resonant zone is when theta equals 0. And that's just simply not the case in higher dimensions. So now, and in many ways, this was the major breakthrough in the paper of Parnowski and Sternberg, is to be able to handle what happens inside that resonance zone in higher dimensions. So again, we're going to be working with the operator H, which is this guy, and V is smooth and periodic, right? And again, what in principle we're interested in is the local density of states, but because it's going to be technically simpler for me, I'm going to focus on the integrated density of states in 2 dimensions. But the ideas involved in doing the integrated density of states are almost the same, right? And I can say with respect to some lattice, now it in principle matters which lattice, although we will see that it doesn't bother us too much. Okay, and right, so just as before, we can reduce the problem to studying this somewhat simpler, well, okay, in some way somewhat simpler operator, where we cut away from the 0 section, namely where the momentum variable is 0. And the first thing we want to do then, as before, is do the gauge transform. So now we need to find our gauge transform operator, so phi, such that e to the I phi, h1 e to the minus I phi is h2 plus some nice smoothing and small remainder, where h2, as before, looks like this plus. Okay, so I'm lying here slightly, but we'll find out why in a second. Plus, now we will really have this object living in the resonance zone. Okay, and so, all right, I'm gonna just tell you something, and then we're gonna ignore it for the rest of the talk. In principle, you remember I had this mu equals mu of h running around in the definition of my symbol classes. Okay, here is where in principle you need that, and what you do is you take mu to be something like either okay, I'm gonna do this 4 to the log 4 of h inverse with the slightly bigger, or 4 to the log 4 h inverse floor. And the point is you need to be able to make 2 choices of this thing, and you'll get in principle 2 different sets of asymptotic expansions depending on this choice, and you have to make sure you can glue them together. This is a technical part of the process. I'm not going to talk about it. I'm just going to pretend, mu is somewhere in the background and we don't worry about it. Okay, so we're going to agree that if I have an asymptotic expansion in the sense of my symbol classes with this type of mu, then I have an asymptotic expansion in terms of only powers of h. Okay, and I don't, I will never say anything about this again, but I feel like I should say that. Okay, so now, what do we want, right? So what we want is we want to get rid of everything outside of the resonance zones. And remember the resonance zones. So if I have, I guess, so remember I can write V is a sum over theta in the dual lattice, little v theta e to the I theta x. All right, and so one of the key things here is that I want to get rid of everything outside resonance zones. And remember, resonance zones morally are when this is 0. Now, it's too much to hope for that you can really get rid of everything except when these things are 0. So you need to thicken them up a little bit. So we're going to try to remove V where theta c is, say, less than h to some power epsilon. Okay, so this is not quite as good as removing this everything but this, but it will be close enough for us. And really what I mean by this is I'm going to remove v theta e to the I theta x where this is true. And one of the features we're going to want is that is a geometric property, which is that if I stare at this and I take theta less than h to the minus delta, okay, delta and epsilon are related somehow, then all of these sets, and again, here I'm taking c roughly 1, look like this, right? So I have my c plane, and I have these tiny little rectangles here near c equal 1. So, and what's important, so here's my circle of radius 1. What's important is that if I take any two of these rectangles which are not the same, then they don't intersect. Okay, that's going to be crucial for us. So these things are really separate. And okay, I will write down, because we're not going to have, I just don't have time to prove it for you, but it's a simple proof, which is that if you have u and v in some lattice without 0, u not parallel to v. Sorry, this is, I should probably not use v. This is a little v. Then, yes, thank you. Then the sine of the angle between u and v is bigger than some uniform constant u v inverse. Okay, so this is enough then, if you stare at it, to realize that if epsilon is smaller than, say, 2 delta, then indeed these will either be the same or separate. Okay. So that's what I need. I need these resonance zones to be in different places. Then that way, again, what's going to happen is we're going to remove everything from the potential between these resonance zones. Right, so I have a whole bunch of resonance zones in principle like this, and I remove everything from the potential. So the only thing left in my operator in these pink zones is this Fourier multiplier. And then in these little white strips, these are the resonance zones. And here I have a trace of v theta, so trace in quotes, right, just something left over, e to the I theta x, where theta is pointing in this direction. Right, so that's what the picture looks like. We're going to try to remove everything in the pink zones, and then we will have something left over here, which is not a Fourier multiplier, but it will come from a function like this, namely something oscillating in the orthogonal direction to the strip. Okay. Okay. So the actual the actual gauge transform construction is very similar then, right? So my gauge transform lemma says what? It says, okay, I'm gonna, again, I have some parameters. We won't worry too much about what they are. Actually, I guess I need a third. And 0, 2 delta less than epsilon less than a half, let's say. And then what we have is there's some phi in psi comp epsilon self-adjoint such that what? Okay, so what do we actually end up with, right? So e to the I phi h1, e to the minus I phi, and also, by the way, this thing is periodic with respect to gamma, such that this thing is h2 again, plus some smoothing remainder, smoothing in small. And h2 looks like the following thing. So it's minus h square Laplace plus h to the 2 minus 2 epsilon m hd. Plus, now I need to finally tell you what this thing in the resonance zone looks like. So it's going to look like some theta less than h to the minus delta. And then I have an op of e theta of xi, e to the I theta x. And I have some nice properties about e theta, okay? And so what I need to know, what I'm going to need to know about e theta, so e theta, everything, so notice, obviously this thing is periodic. And sorry, theta is in gamma prime. But I also need to know that the support of e theta, where is it? Well, it's where theta with xi is less than h to the epsilon. Xi is similar to 1. And finally, e theta is analytic as a function of xi theta perp. Okay, near xi equals 1. Okay, so that's going to be crucial for us. And I'm not, again, because the construction here is almost the same as what we did in one dimension. It's just that I'm forced to, sorry, an e theta, I should say, is an s epsilon comp. And there should be an h to the 2 minus 2 epsilon here. Okay, the construction here is going to be almost the same as what we did in one dimension, with 2 modifications. Okay, one is that I need to observe that if I put VH to be, so this is VH, this is the sum theta less than h to the minus delta, v theta e to the I theta x, then it's easy to check that that v minus vh as a multiplication operator is indeed O of h infinity psi minus infinity. Right, and it's just because these things, these v thetas, are super polynomially decaying, so there's nothing much to worry about there. And so that's going to be true at every step. So in fact, I only need to gauge transform away these frequencies which are less than h to the minus delta, and that's why I can think that all these resonance zones are separated. Okay, that's the first thing. And the second thing is that, again, we need to worry about the resonance zones. Okay, so what that means is, if you remember last time, I just said, all right, so last time in one dimension, we put phi 0, sorry, little phi 0 to be a sum over theta of v hat of theta, okay, with this chi-square of c minus 1 over 2I c theta. That's what we did last time, and we said, okay, well, theta should not be 0. And of course, I should say e to the I theta x. But obviously, this doesn't make any sense, right? Because I've divided by 0 in some places. So what I need to do is I need to put in some cutoff here, which looks like that. Right? Or sorry, 1 minus psi, excuse me. And psi is identically 1 near 0, and psi in CC infinity. Okay, so if we do that, then indeed, this will solve the gauge transform problem, but I'll have something left over, right? So if I think about it for a moment, I put capital phi 0 is op h phi 0, and I stare at what I get here. Well, it looks like what I want. Of course, it still has minus h squared Laplace. It's still, now I have certainly some Fourier multiplier piece. And then I managed to kill off the bits of this thing at top order where psi is identically 0. Right? So I have plus h to the 3 minus 2 epsilon times some remainder, which I won't worry about for the moment, plus, of course, the stuff that I didn't get rid of, right? So h square op psi of h to the minus epsilon theta c e to the I theta x, and then, okay, we have these chi square c minus 1, right? And that's because, remember, if I were to delete this, of course, I would be trying to get rid of all of v. And sorry, I should say there's a sum in theta, and then I should have v theta here. If this was not here, well, other modulo the fact that this is not well defined, then I wouldn't have this term. But because I must stay away from the resonance zones, I must have this term, right? And the crucial observations in order to get these analyticity properties that you want is, of course, notice this doesn't depend on the variable I want analyticity in, so I'm happy. Okay, this is obviously analytic near x equals 1 because it's constant. And I need also this r tilde to have those properties, right? Okay, so this unfortunately doesn't quite follow from the rules that I told you. It's very close. I just need to know that the full symbol of this thing depends only on derivatives of the composition. And once I have that, the analyticity properties will follow. Okay, but now you're in a position to turn the crank, right? You're in a position to do this iterative construction. Remember last time we made some inductive statement that said, okay, I find a phi n, which has this form, except for now I have h to the n minus whatever, h to the 2 plus n, and then I find the next one and the next one and the next one. And at every step, because I know this thing has the good analyticity properties, I know where this thing is supported, I can close the argument. So again, I just simply don't have time to do that today, but I will send around the notes I wrote to do these lectures. They are not polished, just fair warning, but they contain some of the details here. Okay, and you turn the crank and you get this statement. Okay? Any questions before I pretend like we've proved this? Yeah. Yes. These guys? Yes, yes. So this whole, you're asking about the width in this direction, right? So this whole thing is h to the epsilon sized. So the number of, I mean, you know, morally the number of steps is like h to the epsilon minus 1 number of steps that you can take. Right, because each, if you think about it, for a fixed frequency, okay, forget about the fact that I have, in principle, somewhat large frequencies. We have bounded frequency. Then each step is of size h, right? That this got rescaled from your picture where a fixed frequency was size 1 to my picture where a fixed frequency is size h. And I start at the bottom and I just go up by steps of h. Yes, yes. So the whole Fourier picture gets rescaled by h so that I can work in the compact set. Yeah. Other questions? Okay, so I will pretend like we've proved this statement. So this here ends the gauge transform. And now the game is to analyze such an operator, right? In particular, the integrated density of states for such an operator. And to simplify the arguments, I will assume there is exactly one resonance zone. This doesn't really matter, but it will make my life easier. So what I will assume is that I've found, again, my gauge transform operator, and h2 looks like minus h squared Laplacian plus h to the 2 minus, okay, in principle, I think I could put an epsilon here. It doesn't really matter. Let me just do this. Plus h to the 2 minus 2 epsilon. And then I have a sum over n less than h to the minus delta. I have op of en of xi e to the I n x2. And here, the support of en of xi is where xi2 is less than h to the minus epsilon, xi is roughly 1, and en is analytic in xi1 near xi equal 1, right? So the picture is, okay, so I've got my xi space. I've got the circle of radius 1. That's not a very good circle, but there it is. And my resonance zones are here and here. And everything else, I have just a Fourier multiplier. Okay. Okay, so now the reason that life is easier when I compute the integrated density of states is because it's easy to check that, at least in the periodic case, it's easy to check that this is a unitary invariant thing. So because IDS is unitarily invariant, okay, at least for periodic unitary operators. So this is the easy thing to check, although it's true more generally. I only need to compute the IDS for H2. Okay, and the reason this is easy to check in the periodic case is because I can write the IDS at some lambda as an integral over the Floquet block decomposition and accounting function for the Floquet block operators, right? And this thing is obviously unitarily invariant. when you conjugate by periodic unitary operators. Okay, so all this to say, I only compute the IDS for H2. So I forget that I got here by conjugating by some potentially complicated pseudodifferential operator, and I focus on computing the integrated density of states for H2. Okay, so I will not use this formula for the integrated density of states except to justify that this thing is unitarily invariant. Okay. So let us go then. So we have basically two regions, right? We have the region in the pink things, and we have everything else. All right, so I will define a set D. This is the place where the operator is essentially diagonal. And this is just going to be where C2 is bigger than some large constant h to the epsilon, or C minus 1 is bigger than some delta, and R is D complement. Right, so this is just, again, R is for resonance zone, D is for the rest. And I want to be able to decompose my integrated density of states in terms of these two things. Okay, so let's talk about how you do that first. So I want to define projectors corresponding to these two objects, and they're simple to define, right? I just define them on the Fourier side. Same thing. All right, so these are the projectors onto some invariant spaces for my H2 operator. And the upshot is that, so what I mean by that, of course, is that these things commute with H2, right? So that means, of course, these are good candidates for decomposing whatever you want to compute into two pieces. So in this case, they will be good candidates for computing the integrated density of states. Okay. So now, how do I want to think about the integrated density of states? Well, I want to think about it as the following thing, and I'll be always computing it at 1. All right, so this is the limit as r goes to infinity of 1 over pi r squared integral of e h1 delta x dx. Right? Sorry. Okay, so let me put the 2's in. Okay, and so it's natural then to just decompose this inner product in terms of these two projectors. All right, so I will write this as, okay, I'm going to say it's ND H2 1 plus NR H2 1 and N either D slash R of H2 1 is nothing but the limit as r goes to infinity of 1 over pi r squared, then the integral of E H2 1, and then I should stick in either pi d or pi r on both sides. Okay, and because H2 commutes with these projectors, I know that indeed the IDS of H2 1 is nothing but N D H2 1 plus N R H2 1. Okay, so let's see. Let me tell you what happens in the non-resonant zone, so with pi d, and then if there's time we can come back to it, but I don't think there will be. And then we'll spend the rest of the time thinking about NR here. Okay, so the first thing you need to check then is that I can compute ND of H2, 1. Actually, sorry, I realize I made a mistake, which I shouldn't have done. No, okay, I leave it alone for the minute. Yeah. Okay, so I know how to compute this thing. And it looks just like what would happen if this were a Fourier multiplier everywhere, except that I'm only restricted to those covectors which are in this D set. So D stands for diagonal, in case I accidentally say that. So what is this? This is 1 over 2 pi h squared integral eta square plus h to the 2 minus 2 epsilon m of eta less than 1 d eta. And that's it. So if you check, except for that eta should be in D. Okay, so if you check, if I really had honestly a Fourier multiplier, you can compute that the integrated density of states is indeed just the volume of the set where the symbol is less than 1. The only difference here is now, because I've stuck in these projectors here, I'm going to be restricted to covectors which are in inside this D set. Okay. And the reason you can compute this, so I'll just indicate indicate the proof. The point is that if I stare at this thing for just a moment, right, so this is the sort of object I need to understand, because I can move this pi d over to the other side. Well, this is the same thing as pi d e pi d h2 pi d 1 pi d. Okay, and this is a Fourier multiplier. This I can compute its kernel. Okay, so once you realize that, you now go and you write down the kernel of this spectral projector, which you can do because it's a Fourier multiplier. And then you have to pre and post compose with these things. And that's all there is to it. So you'll have to, do the Fourier transform and inverse Fourier transform a number of times, but I think we are all happy with that. Okay, so now let us talk about the resonance zone. So let me say what we're going to do. We're going to look at the resonance zone, and we're going to do so by conjugating by the Fourier transform. So let me define H2 tilde to be indeed the thing you get when you conjugate by the Fourier transform. So I want FH, H2, FH inverse. And you check that this looks like, well, what it should look like. Plus, well, okay, this one I don't understand so easily. So I have sum over n op en of xi e to the I n x 2 f inverse. Right. So the first thing I want to tell you is, what does this thing look like? So, okay, again, it's an easy computation, so I'm not going to do it on the board, but I will tell you what the answer is. So the kernel k of xi eta of op en xi e to the I n x2 conjugated by the Fourier transform is very simple. Okay, and what is it? It's en at xi minus nh. Okay, now this is okay. Let me call it. Shoot, bad notation choice. Okay, sorry. Omega 2 over 2, and then the delta function at eta minus delta plus n h omega 2. And so here omega 2 is just the unit vector 0, 1. Okay, so what it does in a picture is okay, let me do it here. So in a picture, what it does is it takes something, I'm sorry, this should be xc. It takes something at eta. So I have some, here's xc1, xc2. It takes something here at some point, moves it up by nh distance. So moves it up here. This distance is nh. And multiplies it by the value of the symbol in the middle, right? So multiplied by the value of the symbol here in the middle. Right, so this is this point here. Okay, so this thing is just shift and multiply, shift and multiply, and so on. So this whole sum here is a bunch of shifts in the resonance zone. Right, so I have then over each xc1, I have a bunch of points, and I shift from one to the next. Okay, fine. So I know what the kernel of this operator looks like. It's a multiplication operator, right? So that doesn't shift at all. It's just multiply the value by something, plus a bunch of shifts like that. Okay, so how do I compute the integrated density of states for something like this? Well, I really want to think of this as finite dimensional. That's what I want to do. And it's reasonable to hope that you can do that because you can't go from here to somewhere in the middle. You must only go by integer multiples of h. Right? So you have some large but finite number of points here which can talk to one another. So if you want to write that down carefully, what does it mean? Well, this is basically, again, you're going to do some kind of Floquet block decomposition. Okay. And so in particular, now what I want to do is I want to look at, okay, indicator R, H tilde 2, indicator R, right? That's what I get when I also include the projectors on either side of this thing. And I want to write it in a Floquet block decomposition. Okay, so this is H tilde R of K dk. And this K corresponds exactly to this length H sized interval here. So in principle so let me just do that. In principle, I have one of these every H, And I'm just thinking, okay, well, for each value of the vertical parameter here, I have an operator which acts on these discrete things. Okay, so that's what we're going to do. Okay, so now what I want to do is I want to realize this. This is a direct integral in some sense. Okay, this is sort of in quotes. And we realize this using some family of some unitary transformation, right? That's how you have to do this. So I'm going to take I, which is C2 less than some large multiple of h to the epsilon. And I'm going to make a unitary transformation, which takes me from L2 of R cross I to L2 of R with values in L2 of 0h to some large integer power. All right, this is the realization of the Floquet-Bach decomposition, and n here is just, okay, the ceiling function applied to mh to the epsilon minus 1. Okay, so that's the number of dots here. Okay, and you can write down explicitly what this unitary operator is, right? So it's not hard to do. You can just say, okay, u of k C1 applied to some function. The jth component is nothing but f of C1 and then C2 plus JH. Right, and that's your unitary transformation. So you check for yourselves that this is indeed unitary. Right, but again, this is the same thing you would do, right? If you have a nice periodic operator, you do Floquet-Bach decomposition, and you get to identify a bunch of spaces, which is what you want. Right, you get to separate this thing into a direct integral of spaces. Okay, and now you check. So u of k C1, h tilde 2, maybe with some decoration, is gonna be some nice thing like this. Okay, it's a operator which depends on k and C1, u of k C1 u. So I don't need this. What does this h tilde look like? Well, it's a big matrix, 2n by 2n matrix. Sorry, this should be 2n, I suppose. 2n by 2n matrix for each value of k and C1. Right, and what it looks like is it looks like C1 squared times the identity plus the diagonal matrix formed by k plus jh squared plus, okay, h to the 2 minus 2 epsilon times some diagonal matrix. I won't worry about what it is, but it's m. Oh, okay, I can write it down. M of C1, C2 plus, sorry, k plus jh, excuse me. Okay, plus the part that comes from these shifts. Right. So what does it look like? It looks like plus h to the 2 minus 2 epsilon e I minus j at C1 plus I minus j over 2h omega 2. Right, and that's the ijth coordinate of the thing, right? So this is what you get. It doesn't really matter that much, but what matters is that you have a finite dimensional matrix. You know what the main part of it is. It's this C1 squared times the identity plus a bunch of smaller stuff. That's what really matters. And you know that this EI minus J is analytic in C1, and also this thing is analytic in C1 near 1. Okay. I think we can do it. I think we can get there. Okay, so now I need to write then the integrated density of states for this resonant zone, or for the two pair of resonant zones, in terms of something about this operator. Okay, so now what we're going to see, okay, so I think I'm going to do the thing where I tell you this, and then if we have time, we go back to it, because I want to make sure I get to the end. But this, you can check that this NR of H2 at 1 is exactly 1 over 2 pi H squared. An integral like this, then the trace of H tilde R of K C1. Sorry, there should be a trace of now the spectral projector for this thing at 1, and then dk dc1. Okay, so now of course I'm lying slightly because I need to stay inside my. I'm double counting something here, so I should be honest. So I had this circle, right, and I told you the resonance zones were here and here, and then I said, okay, this is R, but this is not quite true, really, because now I'm double. When I do something, when I have this integral over all C1, I'm double counting the middle here. So I have to make a choice about, so this is getting double counted in this integral. So I have to make a choice. It's not very important, but I have to make a choice into which thing I put this. Okay. I mean, and the reason that it's not an issue is because here in this region, this E is 0. Right, so you really have a Fourier multiplier. So there's no issue with figuring out what this integral does there. So I'm going to actually ignore this fact and just pretend that this formula is really correct. Okay, so now what's going to happen? What's going to save us here? What's going to save us is that this matrix in these two little regions is monotone in C1. So if I increase C1, the whole matrix increases. In particular, all of its eigenvalues increase. Okay. So crucial fact, and this is really, genuinely important and the key thing which makes this analysis go. If I start shifting in C1 here, start moving to the right, which corresponds, remember, if you like, moving these dots to the right, then indeed this matrix increases. Okay. So why is that useful? So now what I want to do, so this H tilde R is monotone in C1. Okay, again, now I will forget about, I either have C1 near 1 or C1 near -1, and they're monotone in opposite directions. Okay. And so that one thing that lets me do is, this is a matrix. It has some finite number of eigenvalues. I can always solve the problem lambda j of h tilde r k at plus minus tau j plus minus of 1, in fact, I get rid of the 1 altogether, is equal to 1. Right? And here, there's a unique solution now with plus minus tau j close to either plus or minus 1. And that's where the monotonicity, one place the monotonicity comes in, right? So because I know if you check, if you're here, so 1 is somewhere here, and minus 1 is somewhere here. If I'm to the left, I know that this matrix is really less than 1. If I'm to the right, I know this matrix is really bigger than 1. So I can find such a solution. Okay, and now I want to use those numbers to write this integrated density of states. Okay, so this, if you think about it, right, this is the value of C1 where the eigenvalue equals 1. And if you think about it again using monotonicity, if I'm integrating in C1 and I want to know, okay, this is the sum of the eigenvalues, right? Or the sum of the eigenvalues of this thing. So the number of this thing has eigenvalues either 1 or 0 because it's a projector, this E. And it's 1 if the eigenvalue is in C1 if the eigenvalue is less than 1, and 0 if it's bigger than 1, right? So those are the eigenvalues. So I can write this integral in a nice way. In particular, I can write it as a sum. This is equal to 1 over 2 pi h squared, sum over plus, minus, and j of the integral from 0 to h of tau j plus minus of k dk. Right? It's because, again, I count a 1 as long as the eigenvalue is less than 1, it crosses at tau j, and then I get it counting as 0. Right? That's how this integral looks like. So what I really need to compute then is this thing. Oh dear. All right. So let's do it. So far, I haven't used analyticity, right? So obviously now is the moment to use analyticity. When I want to compute the zeros of some function, analyticity is probably a useful feature. And here's where it's going to come. Okay, so what we do is we take, again, here, this is the C1 plane, but now I complexify everything. So this is the real part of C1 and the imaginary part of C1. And then here's 1 and minus 1. And I take contours like this. Right, and I'm interested in the zeros of a certain function. Right, so this is gamma plus and gamma minus. I'm interested in the zeros of, the eigenvalues of this operator. So I'm interested in the zeros of the function f of z and k, which is what? Which is the determinant now. I can take the determinant. This is a nice matrix of h tilde r of k z minus 1, right? That's what I'm interested in. I want to know the number of zeros, or I want to know something about the zeros of f of zk inside gamma plus minus. Right, those are, in fact, the tau j's, right? So, okay, you could be worried. We have a bunch of zeros here somewhere. But a priori, you might have zeros up here, right? So you might have zeros inside this contour that are not on the real axis, right? We're interested in the real zeros of this thing. Okay, so, but it's easy to compute the number of zeros of f of zk inside the contour. You use Cauchy integral formula, all right, and you write this as 1 over 2 pi I integral over gamma plus minus of f prime of z over f of z dz. Okay, now this is a, you know, I can use, what's the name of the formula anyway? You can compute the derivative of a determinant. It involves the trace of something. All right, so it's equal to 1 over 2 pi I now. This whole thing becomes a trace of this h tilde, sorry, hr tilde of kz, okay, prime, right? So I take the derivative in z, and then I have hr tilde kz minus 1 inverse dz. Okay, and you can check that this thing so you check because of the form, which, okay, it's still here. Maybe I keep that. Yeah, I swear I'm almost done. Okay, you check that this looks like what it would look like if you just had the identity. So you would get 2z squared identity, sorry, 2z identity trace plus an error. And then 2z squared identity minus omega inverse dz, again, plus an error. And the point is this whole integral is integer valued, and the small stuff here is less than an integer. So you check that this is equal to 2n. And so the only zeros are the ones on the real axis. Okay, so now, unfortunately, I will write the formula for you, and then I will stop. Okay, so what we really wanted to know was a sum over j and plus minus of tau j plus minus. And we write that using exactly the same type of formula, right? Using the Cauchy integral formula, but now multiplying by z, right? So 1 over 2 pi I integral of z, f prime of z, f of z, dz. So this has a sum plus minus, gamma plus minus. Okay, and now I don't have time to show you how it happens, but I will write the last formula. Sorry, Charles, I know I'm late, but hopefully you can forgive me for going 3 minutes late in 5 hours. H tilde kz minus z squared I. So this is the part which is not just z squared times the identity. And you get a big sum like this. It's a sum over plus minus, and then sum over L, 1 over L factorial, d xc1 to the L of a trace of 2xc1 square plus xc1, the derivative of this ER, and then minus 1 to the L, and xc1 plus minus 1, minus L minus 1, ER to the L. Okay, and that comes from just expanding the inverse that you get here, right? The inverse you have here using Neumann's series, and then reevaluating using the Cauchy integral formula. And now everything in sight here has an asymptotic expansion in powers of h. And so therefore the whole sum has an asymptotic expansion in powers of h. Okay, sorry, thanks for the time. I'll stop there. So nobody understood. Jean, yes. Okay, so I mean, one can get away in principle without using this flow K decomposition into a finite dimensional thing by approximating by finite dimensional things. So that sort of can get you out of the world of periodic operators using this methods. And indeed out of the world of quasi-periodic operators, we believe. But I don't know how well this could work if you have real geometry, if you have curved trajectories. I mean, there are other methods we're hoping to use, but not this one, I think. Yeah, Jacob. Yes. Well, right. That's one of the obvious things you want to do. And indeed, that's one of the things we're trying to do. But, you know, the methods really don't mix well. So you have to really think about how to do that. Yeah. Yeah. Analyticity, a miracle. Yeah. Yeah. Yeah.